This video will show you how to set up a parameter estimation problem in COMSOL where there are 2 points where data are measured. You can see the geometry up here and the 2 points are right there. And so there's a boundary condition there. We're going to put in heat, and the heat will propagate from left to right. And we'll measure the temperature at those 2 reference points. And the data that we would measure from those points are shown over here on these columns. So those are the locations, the X and Y locations. That's the temperature that's measured at the point, and the A column is the time. So if we scroll down, we see at the green bar that the location data has changed from 0.08 to 0.02, so that's the second. This is a plot of the data. This is the concentration as a function of time. And these data here were measured at that point. These data here were measured at that point. And these are the data that we're going to want to fit with the model, and we'll use that fit to estimate the diffusivity. So here's the model. I've already set it up, so let me just go through how it's put together. So there are 2 domains, a square domain and then that rectangular domain to create the region on the left side. And I put in 2 point probes, and these are what I use to generate the data. We're not going to use these in the inversion, but this is how I generated the forward model. And here's the physics. Diffusion, I don't have that convection checked, so it's just diffusion. And I have for the diffusion coefficient that on the left box it's D11, and on the right box it's D22. So those are the 2 diffusion coefficients, and those are set up as global parameters up there. That's what we're going to want to measure, or going to want to estimate, those 2 parameters. And then just default boundaries, except on the left side is a concentration boundary. Initial conditions are 0. We set the concentration on the left boundary to 1. The objective function is set up here in this optimization node, and it's already set up here, but let me show you how to do that. If we go to add physics, down here to mathematics, optimization and sensitivity, and general optimization. So we put in a general optimization node, and then we right click on that and go to least squares objective, and then right click on that, and we're going to need to put in labels for the different columns in the data file that we're going to import. And we saw that earlier. There are 4 columns. The first column is the time column, and then there's a coordinate, there's another coordinate, XY coordinates, and then the last one is the value, which will be the concentrations. So we put those in, and then we need to set up the variables. So we go here, and that's the X coordinate, which is what we want. This is the Y coordinate, and the value is the last column is the value column, and that's labeled as C, which is the dependent variable concentration for the diffusion problem. And then to complete this setup, we need to give it the file name. And let's see, the file name we entered here, and there's the file name for the file that we want to use. And let's see, let's check and make sure this is being applied to the domains. That should do it. So now we're going to go to the study, and what I've done is to put in a parameter estimation node. It's right there. And when I put that in, I have to populate it. So under data source, I select least squares objective, and the least squares objective is that physics node there. And then I need to put in the parameters. So these need to be global parameters. I select them and I give initial values and then a scale, which is going to be similar to the initial values, and then a lower and an upper bound. Need to set the range of the time-dependent model. And then I let it run. And the analysis tries different values and calculates the residual, the sum of squared residuals between the predicted and observed, and then it goes to find the best solution. You can see the objective function here. This is the sum of squared residuals, and that number is getting smaller as the solution converges on the data. Then it's complete. The analysis has converged, and there's the final plot. Fits the data pretty well. And what we also want to do is take a look at the objective table. The objective function is the sum of squared residuals between the predicted and observed. And if we go down to the physics node, you can see I check keep objective values, and it's objective table 12. And I go to objective table 12, and there it is. This is what we saw scrolling by during the run, and we get access now to all the different trials that the parameter estimation routine used, and then the final one when it converged, and has a sum of squared residuals of 10 to the minus 6 at the end. So there's another way to set this kind of problem up, and that's as an optimization problem, where we go and select optimization and optimization here instead of parameter estimation. There's what we used before. Now we're going to set it up as an optimization problem. This has more versatility than parameter estimation, but we're going to set it up essentially as a parameter estimation problem. So the objective function that we set up there in the least squares objective, we're going to use that. We're going to identify the parameters, and we need to have initial value scales and the upper and lower bounds. All that stuff there is just defaults, and then the output that we're going to generate. In that output, I've identified this particular plot, and I set this plot up to show the data and the current value of the predicted temperatures, or I guess probably concentrations rather than temperature. So there it's converged, and then we get the file with the objective function. And then one thing we should keep in mind is we used this, let me see, there it is, the Babiqua method of parameter estimation. There are a variety of others. Some work better than others, some are faster than others, so you should try out different methods. Under optimization, we also have different methods. See that one Nelder-Mead at the top? That works pretty well. That's one of the faster methods. It's only available in optimization. So there you go. Give it a try.